Welcome you all to a new edition of physics. In this edition, we'll revise the first 3 chapters of electricity. You will be encountered with miscellaneous questions of gradual difficulty, multiple choices, and we'll try to solve some problems. So let's get started. The first question: mention an application on each of the following, or application of each of the following. Okay, we want an application on mutual induction. Okay, we want a device which based on mutual induction. Its function is based on mutual induction. As a matter of fact, we've got 2 devices. Okay, transformer and induction coil. Okay, application on self-induction. Can you tell? I guess all of you know it. It is the fluorescent lamp. It is the fluorescent lamps. Okay, application on eddy currents. Okay, I guess it's all easy for you. Eddy currents are used, yes, thank you very much, in induction furnaces. They are used in induction furnaces. Okay, and an application in electromagnetic induction. I'll give you 2 seconds to think of it. A device whose function is based on electromagnetic induction. I believe it's all easy for you. It is the AC dynamo. It is the dynamo. Okay. Also, we want an application on magnetic torque. It could be, or application on magnetic effect of the electric current. You know, we've got a lot of devices whose function, yes, depends on magnetic torque, such as, okay, that's right, the moving coil galvanometer, the DC ammeter, the DC voltmeter, ohmmeter, and also the motor. They are all based on magnetic torque, or the magnetic effect of the electric current. Okay. We've got another type of questions. Okay, I think you'll find it interesting and so easy for you. What is the significance of the negative sign in the following relation, in the following expression? We want to know the meaning of the negative sign. Okay. EMF equals negative N delta phi magnetic over delta T. The question asks for the significance of the negative sign. Yes, thank you very much. It refers to Lenz's rule, which states, it refers to Lenz's rule, okay, which states the direction of the induced current must be in a way such as to oppose the change producing the current, such as to oppose the motion. So the negative sign indicates Lenz's rule, which states that the induced current flows in such a direction so as to oppose the motion, or change producing the induced current. Another type of question: write the mathematical relation that expresses. What about this question? We want the rule that expresses a certain situation. Okay, write the mathematical relation that expresses, yes, Ampere's circuit law. It's a little bit strange. You know it? It is the law which determines the expression which determines the magnetic flux density at a point of normal distance d from, yes, current carrying a straight wire. We call it Ampere's circuit law. Can you remember? Okay, I think you can. So magnetic flux density equals mu, which is permeability, I over 2 pi d. Okay. Another, we want the expression that, yes, or the relation that expresses law of conservation of energy. Law of conservation of energy. It is, yes, it is Kirchhoff, or we can say the algebraic sum of all voltages encountered in any loop equals 0. Summation or sum of voltage equals 0. It is Kirchhoff second law or Kirchhoff voltage law. The algebraic sum of all voltages encountered in any loop equals 0. Sum of voltages equals 0. What about the expression? Okay, the relation that expresses law of conservation of a charge. It is the first law. Okay, it says the sum of the currents arriving at any junction, any point, any node in a circuit must equal the sum of the currents leaving that point, or sum of currents equals 0. We can say it in another way. Okay, the algebraic sum of the currents flowing into and out of a junction equals 0 or 0. Sum of currents equals 0. And what about the expression? What about the relation that expresses Ohm's law of a closed circuit? It is very important. We've got two laws for Ohm. Ohm's law applied for a certain item of a circuit, yes, V over I equals R, and Ohm's law for a closed circuit, yes, it is, thank you very much, I equals V battery over R capital plus R small. Current passing through the battery equals, yes, EMF of the battery over total resistance, internal resistance and the external resistance. We call this Ohm's law of closed circuit. Now we've got another type of questions. We've got, yes, a problem. In front of you we've got, yes, two straight wires carrying current I1, and the second current also carries the same current intensity. So the two wires carries the same current intensity. And a single loop means we've got just one turn, carries a current, yes, I2 in, yes, clockwise direction. Okay. The figure shows two long straight wires that carry the same current intensity I1, denoted by I1, but in opposite directions. And this means that the field produced by these two wires in somewhere inside the two wires have the same direction. The two fields have the same direction. And it must be opposite to that of the loop so as to cancel each other. So the wires, your attention please, same current intensity denoted by I1, but in opposite direction, and this makes the field inside the two wires in the same direction, and a loop that carries a current I2, yes, in a clockwise direction. Okay. When a compass is placed at the center of the circular loop, it shows no deflection. And this means the field produced by the two wires, yes, is cancelled by that produced by the loop. And we want you to compare between I1 and I2. So the question, this is a problem. We want the ratio between I1 and I2. Okay. At the center, what happens? As I said, the field or the two fields of the current carrying straight wires, okay, and they are the same, are cancelled by that of the circular loop. Okay, this is quite clear. Now, 2 multiplied mu I1. I1 is the current flowing in the straight wire. Each wire of them carries a current of I1 over 2 pi d. D in this case is the radius. Okay, is equal and opposite to the field produced by the circular coil. Field of the circular coil, permeability mu, Ni2 over 2r. Permeability will be cancelled out, okay, and yes, r will be cancelled out. Now we can say 2I1 over pi equals I2. So the ratio, it's all easy. Now the ratio I1 to I2 is equal to, yes, pi over 2. So we managed to solve the problem. Another problem, and it is on Kirchhoff's laws. In front of you, we've got a circuit, okay? We've got an arm, AB, that contains 1 ohm resistor, arm BC, 2 ohm resistor, and arm CD, 1 ohm resistor, and AD, 1 ohm, yes, resistor. And there is a resistor that connects B and D, okay, and it is also 1 ohm. The bridge is not balanced. This is quite clear. It's not balanced because 1 over 2 is not equal to 1 over 1. The battery, and this is very important to put this into, to bear it into your mind. EMF of the battery is 13 volt and it is of negligible internal resistance. Our internal equals 0. Okay? Use Kirchhoff's law to calculate the value of the current in each resistance. So we want the current that flows, yes, through each resistor and the total current, of course. Okay. Yes. Now we'll do, and we want the equivalent resistance of the circuit so as to be able to, yes, get the total current. Okay. Now your attention, please. Assume that the total current equals X plus Y. Okay, we'll take it one by one. Total current equals X plus Y. What happens to the current at node A? It divides into 2 portions. Portion X that flows through the 1 ohm resistor, the arm AB, and portion Y that flows through the arm AD. Okay, so the current that reaches point B is X. Okay, what happens at B? It will divide. Okay, assume portion of this current of X divides into Z that flows into the 1 ohm resistor at the middle. Okay, and the rest will be X minus Z flowing through the 2 ohm resistor. Okay, great. So once again, let the total current be equal to X plus Y, X and Y. X, yes, will flow through the 1 ohm resistor, Y through the arm AD. And the current at B divides into Z, and the rest of X will flow through the arm BC. And what happens at the, yes, node D? Yes, current Z and current Y, yes, join together, combine, so the current flowing through the arm DC equals Z plus Y. This is very important, and it is the essential step to solve such a problem, and it is not an easy problem. Okay, now we managed to distribute the current. We'll now apply the rules. Okay, in front of you, by applying Kirchhoff voltage law on loop A, B, D, A. Your attention, A, B, D, A. When the current flows, when going with the current through a resistor, we'll have a drop in voltage. Okay, so your attention, will apply Kirchhoff's on A, B, D. Current flows through X, okay, and flows through current Z, flows through the arm BD, but if we go clockwise, will be against the current flowing through, yes, the current Y. Okay, so if we are going clockwise, we are in the same direction as that of the current flowing through arm AB, and that flowing through arm BD, but against the arm AD. Okay, so what about the signs? Thank you very much. Negative X, current equals X, and the value of the resistor 1. 1 times X is X. So as we get in through the resistance, a drop in voltage occurs. So minus X minus Z, 1 times Z, and plus, yes, Y. Okay, this is equation. We can rearrange it. We can say, yes, X plus Z equals Y. This is the first equation. Okay. By applying Kirchhoff, yes, voltage law on loop, yes, A, B, C, E, F, A. A, B, C, E, F, A. This means we are going to apply it on the entire circuit. Okay? Your attention will do the same. So, minus X. Okay. When passing through the branch BC, what happens? Okay, we are going in the same direction of the current. So we expect a drop in voltage. So negative 2 is the value of the resistance times the current X minus Z. Okay, plus 13. Why plus 13? Because EMF is pushing, EMF of the cell is pushing in the same direction. Okay, we'll rearrange it. So 2Z minus 3X plus 13 equals 0, and this is the second equation. Okay, now I know it is a little bit, yes, difficult, but be more patient, please. By applying Kirchhoff voltage law on loop BCDB, BCDB, now it is clear for you? Yes, great. Negative 2 is the value of the resistance, times the current X minus Z, yes, plus Z plus Y. Why? Because we are going against the current. All X equal to 0, we'll rearrange it. So X equals to Z plus half Y. Now it's a pure matter of math. Okay, physics, yes, come to an end now. It is, we've got equations. We have to solve these equations. Okay. Substituting for X in equation 1, we'll obtain that Y will be equal to 6Z. Substitution for Y in equation 3, X will be equal to 5Z. Okay. And substituting for X and Y in equation 1, we'll obtain the value of the current, yes, Z, it is 1 ampere. It's so easy now to get Y. It is 6 ampere, so X must be equal to 5, and X plus Y is 11. R equivalent equals the total voltage, which is 13 over the total current, 11, so it is 1.1818. We managed to solve it, and it is, I know it is a little bit hard. Okay. Another problem, and it is very important, a rectangular coil of 100 turns. Okay, try to remember, number of turns is 100. Has a length of 20 centimeters and width of 10 centimeters. Both should be converted into meter. Okay. Is rotated about an axis parallel to the length of the coil. Is rotated about an axis parallel to the length of the coil. Okay? The coil rotates at a speed 3000 rev per minute. 3000 rev per minute means revolution per minute. Okay, you know, quite sure, I'm sure that you know we should work rev per second. So this figure should be divided by 60. In a uniform field of density 0.28 Web per meter squared, Web per meter squared is the Tesla. Okay, it is the unit, desired unit. Okay, so the magnetic flux density equals 0.28. Now we want to calculate the maximum EMF induced. The maximum EMF induced. Okay, we'll do it, yes, one by one. What about the rule that gives EMF maximum? Yes, it is equal to NAB omega. And what about omega? Omega is the angular speed. It is equal to 2 pi f. Okay. Now, substituting in the expression NBA omega, number of turns 100, magnetic flux density 0.28, area your attention 0.2 times 0.1. It was 10 centimeter and 20 centimeter. So they have to be converted into meters. Okay, multiplied by 2 pi f, frequency is 60. How did you know that the frequency equals 60? 3,600 divided by 60. So maximum EMF, and bear this into your mind, EMF maximum equals 176 volt. Okay. Describe the position. This is very interesting and intelligent question. Describe the position of the coil with respect to the field lines after 5 milliseconds from the vertical position. So, your attention please, we are starting from the vertical position. So instantaneous EMF will be equal to EMF maximum sine the angle. If we are starting from the horizontal, we should use cosine the angle. We are starting from the vertical position, and time is given 5 milliseconds. Milliseconds should be converted into times 10 power negative 3. And maximum voltage, we've managed to obtain it. Okay, so we'll apply instantaneous EMF equals EMF maximum sine theta. Okay, and what about theta? Yes, great. It is equal to 2 pi ft. Pi here is equal to 180. It is an angle. Okay. And the time? What about the time? Time is given 5 milliseconds. Your attention, please. Okay, when we calculate this using your calculator, we'll find the final result 176. Do you remember 176 is the maximum EMF? And what this tell you? Okay, this is very important. It means the coil is placed in the horizontal position where the magnetic field is parallel to the plane of the coil. Magnetic field lines, yes, are parallel to the plane of the coil. How did you know? Because we've got the maximum EMF, which is 176. Okay, another question on the same problem. We want the EMF induced when the coil rotates through an angle 60 from its last position. Okay, now we've reached the horizontal position, so we can use cosine 60 or, thank you very much, sine 60 plus 90. Okay, okay, we'll do it. Yes, once again, how to obtain this? The last position was the horizontal position. Okay, so I can use sine, but instead of 60, I'll add 90. 90 plus 60, it will be 88. And we can use the formula in instantaneous EMF is equal to, yes, 176, the maximum cosine 60, and it will give the same result. Okay, the same answer. Okay, sure. Still working on the same problem. We want effective value, and it is clear cut. It is simple, so easy for you. Okay, effective value equals maximum times 0.707. Maximum equals 176. Okay. Another item. We want the average EMF induced. Average EMF induced as the coil rotates through a quarter revolution. Okay, what about the rule that gives average EMF? Okay, it is Faraday's law. EMF average equals NBA for F. NAB for F. Okay, so it is 100 times magnetic flux 0.28 times area 0.2, 0.1. Okay, for the rule, okay, frequency given 50. So we'll obtain, yes, 112 volt, and the negative sign, as I said, indicates Lenz's rule. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Stay blessed, stay safe. Thank you very much.